Assalamualaikum and good morning. Today, we from Group Alpha represent our final project for subject Finite Element Method SEMM 3033. My name is Muhammad Daniel Kabir Abdul Jalil and I will be the first presenter for my group. First of all, I will introduce my group member, starting with our leader Muhammad Afiq Irfan bin Muhammad Shimiri. Next member is Muhammad Suhail Azmi bin Saifulizan. Without further ado, I will start the presentation with short introduction. Next. The objective of this project is to compare the manual calculation and software analysis. The second objective is to recognize that finite element method model can be simplified due to model symmetry by applying appropriate boundary condition. Next, in this project, we need to analyze the deformation of notch thin plate in x and y direction. The suitable method used to analyze this object is constant strain triangle method. In this, it is because in CST, each node only has 2 degrees of freedom, which are in x and y direction. Thus, it makes CST is more suitable method to solve this problem. In CST, it has two types of problem, which are plane stress and strain problem, and strain plane problem. In this project, stress plane project is used because the thickness of object is too small and it's not valid to use strain plane to solve this problem. Next, acknowledge the shape of the end force applied to the object is symmetry. Thus, quantum model can be used to reduce complexity of solution. After applying quantum model, an appropriate boundary condition should be applied at left side and bottom part of the object, which will make the displacement in y direction is 0 for node 1, 2, 5, and 7, and displacement in x direction also 0 for node 1, 3, and 12. The material that you use in the object is steel with Young modulus of 207 gigapascal and Poisson ratio of 0.3. Next, we will continue this presentation with second presenter.
Alright, in this project, two analyses has been made. First is by manual analysis through Octave, and second analysis is using software, which is ANSYS. From this table, the displacement values at point A, B, and C are shown in different units, in which ANSYS is in millimeter and manual calculation, which is Octave in meter. However, both value of results are similar. Firstly, it is because the number of elements being discretized in both analyses are similar, which are 12 triangular elements. Next, the boundary condition that's set up on both analyses also similar, which are at the same point Q1, Q2, Q4, Q5, Q10, Q14, and Q23 are equal to 0. In addition, both analyses are done in plane stress condition. Therefore, it will lead to the same result. Next, the result obtained from ANSYS can be improved by using the optimal number of elements. The reason to find the number of optimal number is to find the convergence of answer to the exact value. Theoretically, the result is more accurate when using higher number of elements. Therefore, we use a graph of displacement x at point B against number of elements. From the graph, we can see the pattern of line graph become linear at 4,000 number of elements. Hence, we concluded at 4,000 of elements, the value of displacement converge at exact value, and 4,000 element is the optimum number of elements to be matched in this problem. Based on this table, The value obtained are not similar when compared to the question number 2. This is because in question 2, we discretize the number of element into 12 number of element, while in this table we discretize into 4,000 number of elements. By increasing the number of elements, the number of nodes also increases. And when the number of elements is increased, the smaller the mesh size, which help to produce more accurate final answer.
Satu lari tu.
However, in our project, 12 elements is reasonable to save the time and avoid tedious calculation in this project. Next, I will pass to the third presenter, which is Muhammad Afiq Irfan.
Dah. Okay, first of all, a very good day. My name is Muhammad Afiq Irfan. So for Poisson ratio, it can be defined as the ratio of the change in width to the change in length. When a deformable body is subjected to axial tensile force, it is not only elongated but it also contract. For example, if a rubber band is stretched, it can be noted that both the thickness and width of the band are decreased. Okay, then mathematically, it can be written as lateral contraction, which is strain in y direction, divided by longitudinal elongation, which is strain in x direction. To calculate Poisson ratio in this project, the average strain x is 2.831 to the power 10 to the power of negative 4, while the average for strain y is negative 8.3 10 to the power of negative 5. This value is obtained from ANSYS software, and therefore we calculate the Poisson ratio is 0.3. The calculated value of Poisson ratio is similar to one used for analysis, which is 0.3. This is because the material used in both analysis is stainless steel. So therefore, Poisson ratio is a material property and it remains constant. Okay, next. Okay, next we evaluate the stress concentration. So stress concentration is responsible for many failure of structure member. For this case, a stress concentration will cause the material to crack if stress exceed the material endurance limit. We define K as a ratio of maximum stress to average normal stress acting at the cross section. Okay, in this project, the stress concentration factor of notch thin plate is being analyzed. Okay, from ANSYS, the maximum stress obtained is 104.5 megapascal as shown in figure, and the average normal stress acting at cross section is 66.667 megapascal. Therefore, the stress concentration is 1.57. However, from the graphical data, the stress concentration is equal to approximately 1.6. The value is slightly different with percentage error of 1.91%, which is quite small, and therefore we conclude that both values are accepted considering of low percentage error. Okay, next. For discrepancies, the result is imprecise in this project because only 12 elements are used. So, local phase element size are larger than the global maximum size. This will cause bad quality elements. The error is huge due to the significant difference in triangular element size. However, large mesh are recommended for initial trial to check data and reasonable result. When a finite element problem is solved repeatedly by increasing number of elements, the mesh is refined and therefore the discrepancies can be eliminated by using the optimum number of elements. Okay, that's all from us and thank you.